Today we're going to practice related rates word problems. Now, just to refresh, a related rate, for example, is when you're filling a balloon with air. And the radius has a rate of change because it's growing, and the volume has a rate of change because it's also increasing. And these two different rates of change are related because they both relate to the balloon, they relate to each other. It's just differentiation, but it requires to think about the concept a little bit differently. So I've drawn our square, and the question that we're gonna look at today is we have a square, one side of which is increasing at a rate of 6 centimeters per second. So that's just one side, okay? What we wanna find is the rate of the area of the square, the rate of the area of the square's increase. So at what rate is the square area increasing when the area of the square is 16 centimeters squared? So what we know is that A, oh, I don't have the right color, is that A, and I don't think I have the right, there we go. A is 16 centimeters squared right now. Actually, I'm not going to write that here. I'm going to write that when we write our solution. I'm going to write it in the correct notation underneath it. Well, the most general things that we know right now is that a square is one side times the other side, which is the same, so it's s squared. And we know the change in rate, the rate of change of one of the sides. So that's ds by dt, right? The change in rate, the change in side of the change in time is 6 centimeters squared. Sorry, over s. Okay, so let's just okay. Let's just bound those really quickly. And then we're gonna move on to what we're trying to find. Okay, I'm gonna write it over here. Our solution is gonna be over here. It's not a lot of math, actually. This question isn't gonna require a lot of math. We're looking for dA by dt, which is the change in the area over the change in time. And we're looking for this not just in general, but we're looking at this when A is 16 centimeters squared, which means, and this is what's important because this isn't given per se, but when we think about it, it's given, which means that S is 4 centimeters. And since we're dealing with just one side here, because we have the rate of the change rate of one side, we're going to need the length of just one side. So write that down, keep that in the back of your minds when we implicitly differentiate our formula, which is A equals S squared. Well, we're going to differentiate both sides of this because we're looking for dA by dt, right? That's supposed to be an A. We're looking for dA by dt, which means we need to differentiate the other side as well. So we're doing the change in S squared over the change in time. But now we have a variable mismatch. S is not t, right? So what do we need? We need the chain rule. And if you recall, we're just gonna differentiate S squared with respect to S. So we're gonna have S squared with respect to S, and we're gonna multiply that by S with respect to t. So we know what this is. We know that this is 6 centimeters per second, and we know that this is gonna be 2S, okay? So in our solution, we're just going to plug in S. Well, we know what S is. S is 4 because we've been given the area. So our solution is going to be, let me put it in here and then write the solution there. I don't have that much space. So we're actually going to make this 2 times 4 centimeters times 6 centimeters per second, which becomes 48, and now we're just multiplying, 48 centimeters squared per second. That is the change, that is the rate of the area's increase when the area is 16 centimeters squared. And that's our solution.